y'all. So today I'm just going to be going over the group work from, this is 222 recitation group work. I'm not going to do the argumentation stuff because we already went over that in class. The biggest thing to take away from that is just that if you're answering a free response type question, you really should answer with a fully formed argument instead of just like listing out bullet points, reasons, or whatever. We really want you to be able to give a reason for your answer, give your answer, and then like a solid construction of evidence for why that's your answer. Okay, so now we'll just start with nomenclature. So the big thing here is I will find the parent chain and then add the substituents in, but somebody gave me this good for remembering ortho, meta, para. I'm always just like ortho, meta, para. But if on the top here you put R for like an R group, it spells romp, so you can remember the order that way. I usually just think ortho, meta, para, but this is a really good one. Okay, so draw the structure of the following compounds: dibromobenzene. So I'll start with benzene and put a bromo at the 1 position, and then ortho, meta, it goes right there. For nitrotoluene, so if it's 3 nitro, then toluene must be 1, so that's the parent chain, and then 1, 2, 3. So that is the difference between these two, is for meta, that you start ortho, meta, para here, but if you have the numbers, it starts right here on the first substituent. So that's kind of slightly different. Like this isn't ortho starting from here. Also, sorry if you can hear the keyboard in the background. My husband is working next to me. We have a small desk, a small office, so. And this could also be renamed meta-nitrotoluene. And also, if you've ever heard of TNT like explosives, I'm pretty sure that's trinitrotoluene. So now you know what TNT is, trinitrotoluene. You know the official nomenclature system. For C-dimethylphenol, so phenol is OH, and I think that this is a good time to remind you the difference between phenol, phenyl, and benzyl. So phenol is this structure right here. It's a parent chain. It has an OH on it. Phenyl and benzyl, the YL tells you these are both substituents. So if you have a longer parent chain, off of that parent chain, if you have a direct attachment of a benzyl, or of a benzene, that's a phenyl. So this would be 2-phenyl nonane, right? If it has a bend in it before it gets to the benzene, so see how this is like CH2 and then a benzene? This would technically be called benzyl. So this overall structure would be 2-phenyl, 4-benzyl nonane. So be sure that you know the difference between benzyl, phenyl, and phenol, because they all can sound really similar, but they have different meanings. Okay, so let's see. We were on C. That's where we got that from. So this phenol is going to be 1. So 2 would be a methyl. 3, 4, 5, 6. And you can't use ortho, meta, para here. You can only use ortho, meta, para if there's 2 total substituents. So if it was just these 2, it would be ortho methyl phenol. But because there's 2 substituents, 3 total, it's 2,6-dimethyl-phenol. Okay, pentene. So cyclopentane is like this. If it ends with E and E, that means it has 1 double bond. And double bonds have higher priority than halogens. So that must be 1, 2, 3, 4, 5. So it's 3,3-dichloropentene. 1, 2, 3, 3-dichloropentene. So that's what I get for D. For E, so this is A, B, C, D. E is orthohydroxybenzoic acid. So hydroxy is an alcohol when it's a substituent. We don't see that very often. Alcohol is usually the parent chain, so it usually comes as a suffix. But when it's the substituent, if you have a higher priority like carboxylic acid, it can also be known as hydroxy. So if it's ortho, then it goes right here, ortho meta para, right? So ortho's right here. So orthohydroxybenzoic acid. This could also be called 1-hydroxy benzoic acid. And then benzene sulfonic acid, that should be one that you memorized. It just looks like this. And then 2,4-dichloroaniline. So aniline, I always get aniline and anisole mixed up, but aniline has 2 N, so that's how I remember it's it's NH2, not NH3, NH2. And then 1, 2 dichloro, so chloro there, 3, 4, 5, and a chloro here. All right, there we go. Now for the trickier part, for this one, we have to name them ourselves. So that one I think is harder. First, identify the parent chain. And be sure to look out for those common names that you memorized. Then find the substituents and then combine it all in the proper order. So this is just benzene, so that's nice. And this is cyclohexane. Hopefully you know that. So here we have something different. You have to identify the parent chain. So either you can find the longest chain, but you have to make sure it has the highest priority. So luckily this is appearing as both the longest chain and it has a carboxylic acid, which is high priority, higher than like an aromatic ring. So this right here is octane, sorry. And then because it has the carboxylic acid, that must mean it's octanoic acid. But you cannot tell what that says. I'll write it down below. Octanoic acid. And then we just have to find our substituents. So this substituent right here is 7-phenyl. And it's phenyl because it's directly attached. If there's a CH2 between this carbon and where the benzene ring started, it would be benzyl. So 7-phenyl octanoic acid. And this right here, that's just phenol. Hopefully you remember that from when we drew it up there. Okay, the next one, 1, 2, 3, 4, 5, 6. So, you should go the other way. I don't know why I numbered it that way. So I guess I'm in the habit of numbering. So first, I recognize this as something we had to memorize, which is benzoic acid. So if that's benzoic acid, then we have 1 methyl group. So we could either say 1, 2, 3. We could say 3-methyl benzoic acid, or we could say meta-benzoic acid. Meta-methyl, sorry, I don't know why. M-methyl benzoic acid. It's very early, so I'm kind of all over the place. Okay, now for this one, there's actually 2 base units that you probably recognize, nitrobenzene and aniline. Either one is fine. I'm just going to go with aniline. I don't think, if this came up on the exam, I feel like it would most likely be a multiple choice question, and there would only be one right answer. So as long as you recognize both the nitro and the aniline, you should be able to get it. But so the base we'll say is aniline. 1, 2, 3, 4. So that would be 2 nitro and then 4 fluoro. But fluoro becomes before nitro because of alphabetical. So altogether it would be 4 fluoro, 2 nitroaniline. And I also think the reason you would go with aniline is because it would make the other substituent smaller if you're ever not sure. Aniline, if you make aniline the base unit, it'd be 2 and 4. But if you made nitro, it would have to be 2, 3, 4, 2 and 5. I think phenol has higher priority than an ester. So phenol is the base unit here. And then 1, 2, 3, 4, 5. If you went the other way, it'd be 1, 2, 3, 4, 5. Okay, so going this way makes them smaller. So 2,6-dimethyl, this is all over the place. Hopefully you can kind of follow along with my writing. 2,6-dimethyl, and then we have, that's 3,6-dimethyl, and then 2-methoxy for this right here. So you combine it all, methox. So the difference is right here, elemento P, Q, R, S, T, V, W, X, Y, because you don't count the di in alphabetical order. So think the methoxy O comes before methyl. So nope, I don't have room here. 2-methoxy, 3,6-dimethyl phenol is the final name there. Let's see. I'm going to draw this one out down here because there was definitely not space for all of this. So let's say for H, we have cyclohexane or benzene, but this cyclohexane has an alcohol in it, so I would say that's the parent chain. Their carbon chains are the same, so the higher priority wins out. So that would be cyclohexanol. Oh, sorry. Sorry, I got that interrupted there. So we have cyclohexanol. And so that makes the alcohol 1, and then the phenyl ring 2. So 2-phenyl, 2-phenyl cyclohexanol. And with this, because the stereochemistry is shown, you should be able to identify if it's R or S. So oxygen's the highest priority, then the benzene ring, and then the straight carbon chain. So 1, 2, 3. So that's R. And then if you come down here, this one also is a stereo center. So 1. The alcohol containing chain would be 1. This carbon containing chain would be 2, and this would be 3. So that also looks like R, but the hydrogen is pointing towards us, not away from us. So we have to flip it. So it would be 1R, 2S, 2-phenyl cyclohexanol. Okay, and now for I. So phenol would be the parent chain. 1, 2, 3. So this would be trinitro, and it's at 2, 3, 4, 5, 6, 2, 4, 6 trinitrophenol. This is benzoic acid. I see the parent chain here. And it's 2-chloro benzoic acid, or also ortho, chlorobenzoic acid. This down here again, phenol would be the parent chain. And then we have 1, 2, 3, 4, 5, 6, 2, 4, 6 substituents. 4 is a methyl. And then 2 and 6 are tert-butyl. So you don't take the tert in the alphabetical order. So it would be 2,6-di-tert-butyl, 4-methyl-phenol. Oh no, I just realized I was off camera, I think just for that one part. I was going so hard. I was like so excited to write it all out. Okay, and then for this last one, actually, because there's an alcohol here, this would be the parent chain. So ethanol is the parent chain because this is the higher priority. Alcohol has to be contained in the parent chain. And so this would be 2-phenyl, it'd be 1-phenyl ethanol. So there you go. That's a lot of nomenclature. All right, so now let's flip over to the back and we'll do some aromaticity. So for aromaticity, I did a short TikTok on this. You can go check it out. But basically, an aromatic ring is more stable than you would expect it to be if it was a normal ring in that structure because it's stabilized by resonance. Antiaromatic rings are less stable, like significantly less stable than you would expect them to be. And non-aromatic just doesn't have the right characteristics. So that's the three definitions. Aromatic has three characteristics that are main. There needs to be an unbroken chain of p orbitals on a ring. There needs to be 4n plus 2 pi electrons, which means basically 2 if n is 0. 4 times 0 is 0 plus 2. If n is 1, it'd be 4 times 1 is 4 plus 2 is 6. If n is 2, 4 times 2 is 8 plus 2 is 10. 10 aniline is an exception to that. If 4 times 3 is 12 plus 2, it'd be 14. So any increment of that should be aromatic. And then it also needs to be planar. And if it has these other two characteristics, the only time it'll be planar are exceptions that you've learned about. So like 10 aniline is one of them. How can you determine? Oh, and then antiaromatic has the same things, but instead of 4n plus 2 pi, it has 4n electrons. And then non-aromatic just will not have a full ring or something like that. It won't have a full ring of p orbitals, like there'll be an sp3 or something like that. You can determine if a compound is aromatic if it has all of these qualities and is not 10 aniline, then that's aromatic. And then I kind of want to give you some practice problems. I'm going to draw them in a different color so you can see them more easily for you to identify if it's aromatic or not aromatic. So here's one. Here's another. And let's do... Okay, so here's some that you'll see a lot. So this is cyclopentadiene, and then you have to ask yourself, is there a p orbital all the way around? So if this is a double bond, then you know it has to be sp2 hybridized, right? There's a hydrogen here, so 1, 2, 3 bonds, 3 sigma bonds means it has an sp2 hybrid orbital, which means there's an unused p orbital that's not used by the hybrid that's making up this double bond. So there's one electron on this side making up the double bond and one p electron on this side making up the double bond. So hopefully you remember that from early on in the chapters. And then right here, this carbocation, hopefully you remember carbocations are flat. When we did SN1 reactions, they'd be flat because it could attack from either side, right? So it's flat because it's sp2 hybridized and there's an empty p orbital right here. So there's an unbroken chain of p orbitals. So criteria 1 is met. Is it 4n plus 2 pi electrons? Well, the pi electrons come from this double bond, and there's one double bond. So that's made up of these 2 electrons, the ones that I showed in these pi orbitals. So yes, there are 2 pi electrons. And if it meets these other 2 and it's not 10 aniline, then it's probably going to be planar. So this is aromatic. This has the same thing. It has a p orbital on each of the double bonds with an electron there and there. And carb anions are interesting. They, the lone pair there can either go into hybridization in an sp3 hybridized, or it could go to a p orbital. It's going to do whichever one makes it more stable. So in this case, if you had these in a p orbital, you'd have 4 pi electrons, which would make it antiaromatic. It's possible that that lone pair would actually go into hybridization and be non-aromatic as well. So those are kind of your options for p. For lone pairs, we'll see more of those in your next group work. Okay, and then here, the next question is, do we have an unbroken chain of electrons? Well, always on a double bond, you know there's a p orbital that's making up this double bond like this, here and here. But this is sp3 hybridized, this carbocation, this too. So this is non-aromatic because it doesn't meet the first criteria. So it's non-aromatic, it doesn't have an unbroken chain of p orbitals. Let's see. So there's 1, 2, 3, 4 p orbital or 5 p orbitals. So it's an unbroken chain. There's 2 pi electrons from this double bond and 2 pi electrons from this double bond, so that's 4, but then there's 2 more in this lone pair. And so if this lone pair goes into the p orbital and is in resonance with the other ones, then you'll have 6 pi electrons. So you have the unbroken chain, you have 4n plus 2 pi electrons, you have 6, and it's not 10 aniline, so it's most likely planar, so this is aromatic. And then right over here, you have a 4-membered ring, cyclobutadiene. It has a p orbital at each carbon, but it has a total of only 4 pi electrons, so this is antiaromatic. So that's kind of how you can tell if something is aromatic, antiaromatic, or non-aromatic. That's just some practice problems that I think will kind of help you get through that. And then last but not least, use the polygon, inscribed, and circle method to determine which of these are aromatic. So I love the polygon and circle method, but the biggest thing you have to remember is one vertex has to be pointing down. So how this works is you pick a place to point down. Any one will do. You draw a circle around it, and then anywhere the point touches, that's a molecular orbital. So I think this is a lot easier than the other molecular orbital theory. So there's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 total. And then right in the middle of this is your, hopefully you remember this from when we did bonding, non-bonding, and anti-bonding, but that's your non-bonding line. And then you fill in your pi electrons. So you have 2, 4, 6, and a lone pair, so 8 pi electrons. Hopefully you know just from the unbroken orbital and the fact that there's 8 pi electrons that this is probably going to be antiaromatic, but you can see the molecular structure as to why. So 1, 2, we're filling in the electrons now. 1, 2, 3, 4, 5, 6, 7, 8. So you have 2 antibonding electrons that are unpaired. So this is not stable. So this is not going to be aromatic. This is antiaromatic. But the cycloheptatrienol cation, it has the same structure. It's the same circle, so you know it has the same 1 point, 2, 3, 4 point total. But it only has 6 pi electrons. So 1, 2, 3, 4, 5, 6, and these are all in bonding, so they're going to be stabilized. So this is bonding. So really all you do with this polygon and circle method, I'll do it with this, this one up here, the I don't know, I can't remember it. Cyclopropenyl ion, I think is what it's called, this one. You pick a point to point down. So let's say we pick this point to point down. Put a circle around it, and anywhere the circle touches the point, that's where there's going to be a molecular orbital. You draw a line right through the middle. This is your non-bonding line. Above it is anti-bonding, and below it is bonding. And then you fill in your pi electrons. So there's 2 pi electrons here. So 1, 2, they're both in bonding. So that shows that these 2 pi electrons are both part of a bonding situation, and they're going to be stabilized because of it. So that's just a few practice problems for you. I hope those are helpful. And if you have any questions, please feel free to reach out to me. Good luck studying.